Hi, in this video, we want to take a look at the Bernoulli distribution. All right, the Bernoulli distribution really is the simplest probability distribution that we can look at. And this is fundamental for building up other distributions. All right, so this random variable is as simple as we could really make it, in that we have two possible outcomes. Either something like yes, no, success, failure, heads, tails, odd, even, male, female, and so on. All right, so how we're going to approach this is that we're going to assume that there is some probability that we are going to get the observation that we will call success. Now, something that's funny about statistics is that we always call success is the observation level that we are looking for. All right, so if I was modeling a disease, and I was to say that modeling the disease is the level that I'm looking for, then success would be having that disease. It's kind of a peculiar thing. So what we're going to do, we're going to code a success with a 1 and a failure with a 0. All right, now, so why do we do this? Well, first and foremost, if I have zeros and ones, if I take the average of the values, that gives me the fraction of success observations, which is very nice for us. Right, so here, so here's a kind of a motivating example. Let's say that we go to an assembly line. I'm going to walk up, and as part of quality assurance, I'm just going to grab an item, and I'm going to inspect it. Now, let's say that there is some probability that that item is defective. All right, well, what I'm going to do, if it is defective, I'm going to put a 1. If it's not defective, I'm going to put a 0. Okay, so if there's the probability of being defective or equal to 1, we're going to go ahead and say that is P. And that's going to be some number between 0 and 1. And the probability of not being defective is going to be the probability that X is equal to 0, which is the same as 1 minus P. Remember, probabilities add up to 1. All right, when we're in this situation where we have just one observation, or so it's one thing that we're looking at, and it's either yes or no, or 0 or 1, or success, failure, something like that, we're going to call this a Bernoulli random variable. All right, so let's look at the probability density function for a Bernoulli random variable. All right, so what we're going to do, we're going to say that the probability of an event is going to be P to the power of the value here times 1 minus P. See if I can get this like that. To the power of 1 minus the value. All right, so what's going on here? All right, so the probability of a 1, I put in 1 for X here and here. So here, if I have a 1 for X, that's just a 1. So, and then if I put a 1 for X, I get a 0 in the exponent. Anything to the power of 0 is 1. So this whole part disappears. And this just becomes P to the 1, which is just P. Okay, so the probability of 1 is P. Now, if I plug in 0, then here, X is equal to 0. And here I plug in X equals 0. Up top in the exponent, I'm going to have a 1. All right, so then this becomes P to the power of 0, which is better known as 1. Here, this part becomes 1 minus P to the power of 1, or 1 minus P, and we get the same thing we have up here. So this is very nice. Now, something that's important to remember about this is that in this situation, for this distribution, only thing that we can observe is a 0 or a 1. That's it. Our parameter value is between 0 and 1. So X is the random variable, and P is the parameter of the distribution. In this situation, our expected value is just P, and our variance is P times 1 minus P. Okay, so this distribution is fundamental towards building up other observations. So what we're going to do in future videos, we're going to take a look at what happens when I do repeated Bernoulli random variables. What happens when I keep on doing Bernoulli random variables until I get a success? Those are different distributions. So remember that in this situation, when x is equal to 1, we call that a success. When x is equal to 0, that's going to be called a failure. And in this coding, when I say success, we refer to that as being a 1, or the level of interest in what's going on. So something that's peculiar about this, if I was modeling a disease with x equals 1, then having the disease would be a success, which is rather morbid, not really how we would normally think about things. So when we're talking about statistics, success failure refers to the random variable, not the actual outcome in terms of interpreting what's going on. All right, so let's take a look at the expected value of Bernoulli random variables. Okay, so remember that when I take an expected value, I take the value times its probability, and then I add them all up. Okay, so in our situation, we have 0 and we have 1. Okay, so when I plug in 0, it will be 0 times the probability of 0, and 1 times the probability of 1. I add them all up, and that's what I get here. So 0 times the probability of 0, and 1 times the probability of 1. All right, well, the probability of 0 is 1 minus p. Boom, we've got that. And the probability of 1 is just p. Boom, we've got that. Now, 0 times anything is 0, so we can drop that. And this is just 1, or this is 1 times p, so it's just p. Boom, we've got it. Okay. So now let's take a look at the expected value as a function on p. Okay, so the expected value, if I look at it, it has just that one p in there. So I can represent this as the expected value as a function on p. Now, this is a very simple function, but this is a good place to start for later distributions that we'll be looking at. All right, so what I want to do in R to visualize this, I'm going to make a sequence of p-values, and I'm going to plot them just so I can visually see what's going on. So I'm going to plot the p-value, and then I'm going to plot the expected value. So y is the expected value, x is the parameter value in the plot. I'm doing a line plot, and here I'm just putting a title on it. Always put titles on your plots. And we can see that it's a simple identity function very nicely when I look at this plot. So it's going from 0 to 1, this direction and in this direction. All right, so now let's take a look at the variance of Bernoulli random variables. All right, so to do this, we're going to use that formula that for variance equals the expected value of x squared minus the expected value of x, all of that squared. So here I'm squaring the expected value. Okay, so a moment ago, we computed that the expected value of x is equal to p. So I know that this part becomes p squared. Okay, so now I need to think about the expected value of x squared. All right, well, if I think about it for a moment, all I'm going to do is I'm going to take each value of x, square it, multiply it by its the probability of x, and I'm going to add them up. Okay, so I'm going to have 0 squared times the probability of 0. I'm going to have 1 squared times the probability of 1. All right, and that's why I have written here with the sigma notation, the summation. All right, so here, remember, when I do the expected value of x squared, I have to square the x. And so I have 0 squared times the probability of 0. I have 1 squared times the probability of 1. And then I'm subtracting the p squared, which is already there. All right, well, this is just 0 because multiplying by 0 gives me 0. This is just p because I'm multiplying by 1. And boom, we've got our variance. And for the last bit, I can go ahead and just factor out a p to get the p times 1 minus p. All right, so now let's go ahead and plot this. So I'm going to do a similar plot to last time. Now, the last one was very, very simple to the point where I think some people won't really realize what the point is, but that's okay. With this plot, the parameter value is on the x-axis. The variance is along the y-axis. I'm doing a line plot. Here is the title of my plot, the variance of Bernoulli random variable by the parameter value. And so now we plot it. Okay, so now something that's very important to notice about this. So it looks like a parabola, and it is a parabola. But wait, there's more. If I look here, this is where it's highest. And I can see that's lowest at the far left and the far right. Okay, let's think about this for a moment. If the probability of 1 was equal to 1, that means every single time we're going to get a 1, do I have any variance? It's always the same. If it's always the same, I have 0 variance, right? In that case, it's down low. I have 0 variance. Now, if the probability of 1 was 0 down here along the x-axis, then I'm going to see 0, 0, 0 every time I look at this, which means I have the same value every single time, which means I have 0 variance. Now let's think about what's happening in the middle. Well, in the middle, if I was going 50-50, there's no like real central, there's no leaning one way or another. It's, you know, there's no like dominant level, there's no dominant value. In this situation, we see that the maximum variance is achieved when p is equal to 1/2, 50-50. Okay, so this is something that is nice for us in statistics, that if I ever need to have like if I'm trying to figure out something that involves like a Bernoulli distribution or binomial distribution, I can always maximize the variance term in terms of the p equals 1/2. And that helps us out on other problems where I'm trying to get to things like sample size. All right, so big takeaway. Maximum variance is when p is equal to 1/2. Minimum variance is when p is equal to 0 or 1. All right, so now I want to talk about density functions, cumulative distribution functions, quantile functions, and random number generators in R. Okay, so the format for R to be doing these 4 functions is that D is for density functions, P is for cumulative distribution functions, Q is for quantiles, R is for random numbers. All right, so here, what we're going to do, if I want Bernoulli distribution, I'm going to grab the binomial function, and I'm going to set size equals to 1. So we're going to take the binomial functions, I'm going to set size equals 1. And that's going to be true for everything that we do for the remainder of this video. If I put D in front of binom, what that is doing, that is saying, hey, I want the density of the binomial distribution. If I put P for probability in front of binom, I'm saying I want the cumulative distribution function for the binomial distribution. If I put Q in front of binom, I want the quantile function for the binomial distribution. And I put R in front of binom, I want a random number generation for the binomial distribution. Okay, so how does this work? So what we do when I'm dealing with the density function, so what this is going to do, this is going to give me the probability of seeing a particular value when I'm dealing with discrete distributions. And so what I'm going to do, I'm going to say, hey, I want the probability of 0, I want the probability of 1 when size is 1, so this says it's Bernoulli, and probability is 50-50. All right, so if it's 50-50, the probability of 0 is 1/2, and the probability of 1 is 1/2, right? And so here we can see that this 50-50 matches 0, 1. This 0.5 corresponds to the probability of 0. This 0.5 corresponds to the probability of 1. Now for our cumulative distribution function, this gives me the probability of being less than or equal to the value I plug in. So here I want to know for what value will give me the probability of being less than what value will it take to be less than or equal to a particular value. And so here I just went ahead and just put down the quantiles, some familiar ones. And so we can see that we have a 50-50 chance of being less than or equal to 0. We have a 50-50 chance of being less than or equal to 0.24. We have a 50-50 chance of being less than or equal to 1/2. We have a 50-50 chance of being less than or equal to 0.075, and we have a probability of 1 of being less than or equal to 1. Huh. All right, so now, why do we keep getting the same value over and over and over? Remember that when I do cumulative distribution functions, it's always less than or equal to. So the probability of being less than or equal to 0.75, well, the only way I can achieve that is if I get a 0. The probability, if I'm going to be less than or equal to 0.5, I have to get 0 from Bernoulli. To get less than or equal to 0.24, I have to have the Bernoulli random variable equal to 0. And so that's why all of these give me the same probabilities. Now the quantile function, this evaluates what value is going to give me a probability comparable to the quantile that I'm putting in. Now with discrete random variables, there are multiple ways to compute this. If you look at the help documentation, it'll flesh out specific details. Here, you can, if you want to, you can start nitpicking stuff and have certain preferences, but just know that this is the quantile function for this distribution. So here, if I plug in 0 for the probability, I see that I get 0. If I plug in 0.24 as my probability, the quantile value is 0. If I plug in 0.5 for the quantile, I get 0. And then for 0.75 and 1 for the probabilities, I see that I get 1 as the quantile. And so we can see that the R function is like splitting the two values in half along the quantile values. Now for the random number generator, what we're going to do, we're going to specify the number of observations we want. This once again says I'm doing Bernoulli distribution, and then the prob gives me the probability of observing a 1. And so here I have a random number generation. I have 30 different zeros and ones. And so where can I use this? I use this in like simulations if I want to verify what's going on, or there's other applications such as like resampling data that I can use. Statisticians use random number generation quite a bit. All right, so now let's dig into an assignment so that we can get our hands on this and get a feel for what's going on. For this assignment, what you need to do, you need to find some event in real life, an actual real world event that has two possible outcomes. And this needs to be something that you can observe repeatedly rather easily. So this could be something like flipping heads on a coin or rolling snake eyes on 2 dice, like something you can do repeatedly rather easily. All right, so what I want you to do, I want you to observe the event 30 times. Okay, so what I'm going to do, if I'm doing a coin, and I'm going to say heads is a 1, I'm going to flip the coin, flip the coin, flip the coin, flip the coin 30 times. Each time I get heads, I put down 1. Each time I get tails, I put down 0. So I'll have at least 30 observations. Now, what I'm going to do after that, I'm going to compute the sample mean and the sample variance of my data. Next, I'm going to plot a histogram of the results. So I'll have a bar graph of how many times I had 0, how many times I have a 1. And now, using my data, I'm going to try and estimate P for that coin, if you choose to flip a coin. Now, next, what I'm going to do, I'm going to run a density, cumulative distribution function, quantile function, and random number generation using my estimated p-value. Basically, just take the code that we just looked at a moment ago, change the p, and rerun it. And then I'm going to put my results into a document and upload it to Canvas. All right, well, that's all I've got for you. Take care and goodbye.